in order to open this file in Google Colab environment. Now for project 4, I need to import some important Python libraries, which are NumPy, Pandas, Matplotlib, and from Matplotlib, I will import style, and I am using a dark background. So let's run this cell in order to import the file. Now all the libraries have been imported. Now it's time to read the data. So in this project 4, I am using the data which is regression underscore data. So this is the same data which I used in project 1, where I implemented simple linear regression with the help of least square. So again here we are going to implement gradient descent on a simple linear regression problem. Simple means that is we have only one feature in our data set. But in order to read the dataset, I need to mount the drive and I need to set the path. So the first important step is to mount the drive. So here I will mount the drive. I will run this cell in order to mount the drive. So Google will ask for the permission. So you have to permit Google so that you are able to mount the drive. Now the drive is being mounted. After the mounting of the drive, we will set a path and then we will be able to read the data. So drive had been mounted. Here we have to refresh. This is drive. Inside the drive, I have a my drive. Inside my drive, course material. Inside course material, there is a folder supervised machine learning. And inside the supervised machine learning, I have regression analysis, where this dataset regression underscore data is present. So since this data is present inside the folder regression analysis, so I have to copy the path of this folder. So I will go to these 3 vertical dots. I will click on that. I will copy the path, and then I will add here another code cell. And then I will type the percentage current directory space, and here I am pasting the path, and I will click on this cell. Now the path has been provided. Now it's time to import the data. So we can see that after mounting the drive and after setting a path, we have successfully imported our data set. So our data set has 2 columns. This is the independent data and this is the dependent data. Independent data means feature and dependent data means target. So we have one feature and one column for a target. Now the next step is to extract separately both the dependent and independent variable. So I am extracting X in a dependent, that is independent variable is known as X, which is my feature. And here I am extracting target, which is my dependent data. So here we have independent data and dependent data, and I can extract both of these. So I am using the same data set in this project, which I have already used in my project 1. Therefore, many of the steps are same initially. Now we want to visualize our data. So we have to plot the scatter plot between X and Y. So this is the same steps of code which we have already seen in our project 1. Let's run this cell. So this is the scatter plot, and we can see that there is a linear relationship exists between the independent data and the dependent data. After this, we have to reshape X and Y. So first we are going to reshape X so that we can transform into a column wise, because we have to then append 1 at the first column of the X. Here I am reshaping X, and here I am transforming Y into a column shape. Here I am creating ones, and here I am appending 1 at the first column of feature matrix. So we can see that this was our feature matrix. These are our feature, and here I have appending 1 because I am going to applying a gradient descent. Now this matrix is known as X input. Previously it is X when we did not append the 1. After the appending of 1 at the first column of this matrix, now we will call it as X input. Now X input has been prepared, and now it's time to apply gradient descent. So this is the equation of a gradient descent we are going to apply. By applying this equation, we have seen this equation, or we have derived this equation in the lecture of gradient descent. So we will apply this equation in order to find the gradient. So this dE by dW, or rate of change of error with respect to W, is a gradient. After calculating the gradient, we will put this gradient value here. This is gradient, which is the same value, and then we will multiply the gradient with alpha, and then we will subtract this product from the old weight to get the updated value of the weight. So here we are going to apply gradient descent. We have already learned that gradient descent is an iterative process. Therefore, we have to apply a for loop in order to perform the iteration. So the first step is we have to initialize the value of weights. The reason is that we have to update the weight matrix. The weight matrix contains the value of a weight and a bias. Since we have only one feature, it means we have only one weight and we have only one bias. So here I am initializing the value of weights with the random value, and then I will run for 3000 iteration, and every iteration or after every iteration, this weight matrix will be updated and we will reach to the optimal value. So here I am initializing np.random.random. This is the size of the weight matrix. So since we have one weight and one bias, the size should be 2 by 1. So the length of x0 is 1. So I am adding a 1 on it. So it will be 1 plus 1, 2, comma 1. So this is the weight matrix whose size should be 2 by 1. That is, there should be 2 rows and 1 column. So here I have put these values in order to get the understanding. Here is the initialization of the weights. Let's run this cell and see what is the shape of the weight and what are the initial values inside this weight matrix. So we can see that this is a weight matrix. It has two random values at the start. And first value is for the bias and second value is for the weight. So in this way, we have initialized the weight matrix. So its size is 2 by 1 because we have one bias and one weight. So here I have initialized the weight matrix. So I have 30 samples. So I need n. If you see, this n is a number of sample. So number of sample is the length of our x or length of our feature. Then I will run the iteration for 3000 times and I have set the learning rate 0.01. Here I am running a for loop and I am calculating the gradient. So this step is basically this. Here is the gradient. So you can confirm this. This is minus 2 over n. So you can see that minus 2 over n, then it is multiplied with this value. Now I have to calculate this value, and this sum is basically a for loop, and through every iteration, we will calculate this. Okay. So the first step is to calculate the term which is inside the bracket y minus xw. So x and w are two matrices. So here we are using dot product of the matrices np dot. This is our x input. X input is our feature matrix. When we appended 1 on it, we call it x input. This is our weight matrix. Then we subtract it from our y, which is our target value. So here we are implementing in this bracket. Basically, we are implementing y minus xw. After calculating, we have to multiply this whole bracket with this x. So here I am multiplying using np dot and I am multiplying x input with this whole bracket. Now this dot capital T is used to transpose x input. So in order to multiply this x inside this bracket, I need to transpose the x so that multiplication is possible. So there are many methods to calculate the transpose. Like we learn in project 1 that one of the method is from NumPy, that is you can use np dot transpose. The other simplest method is you can use dot and capital T in order to perform a transpose. Now, with this step, the gradient has been calculated. After that, I will multiply the gradient with the learning rate, which is 0.01, and I will subtract this product from the initial value of weight, and I will get the update value of the weights. So in this way, in this line of codes, we have implemented the same gradient descent algorithm, which we learned in our previous lecture. So let's run this cell. And here are the value of the weights. So this is the weight matrix. This is the value of a bias, updated value of the bias, and this is the value of weight associated with the feature. Now we have trained our data set using gradient descent. So that was our data set initially, which had 30 samples. We have one independent feature and we have a dependent data, which is the target variable. So we have trained our data set using gradient descent and we have find the optimal value. So you can see that these were the initial value of the weight of the bias and the weight. And after gradient descent, we have the updated or the optimal value of the bias and the weight. Now, it is the time to test the model and evaluate the performance of the model. Since we have used all the training data, we do not have any test sample now. If you remember in project 1, we create our own test data. So we are going to do the same step here. Now I am going to create my test data. So I need 30 samples, or I am going to create 30 samples because I have 30 samples in a training data. This is not necessary that you also generate 30 samples in your test data. So here I am generating a 30 sample. You can generate 10 samples as well. So the minimum value of a test data sample is 0 and the maximum value is 11, and I am generated 30 samples which are linearly spaced, and here I am reshaping it so that I can transform it into a column form. Let's run this cell, and if we want to see our test data, we can add one more code cell and we can see our test data. So we can see that we have generated a test data with minimum value is 0 and the maximum value is 11, and there are 30 samples. Now we need to append one. Now this is very important step. When we use gradient descent, we also need to append one with our test data as well. So here we have created ones. Here we have concatenated ones to our test data. After concatenated ones to our test data along the column, we call it x underscore test. Now the new name of our test data is x underscore test. And here we can see that this is our test data. And here we have appending a 1. Now it's time to get the label for the test samples. So we are generating the label in the same way as we did in project 1 of regression. So I am using np.linear space. I am using the minimum value of y, the maximum value of y. So basically, I am generating the test label with the help of target labels. And I am generating the 30 values because I have 30 samples in my test data. So I call it y underscore test. Now my test data is x underscore test and my test labels are y underscore test. Now it's time to get the predictions from our trained model. So to get the predictions, we know that we need to multiply these two matrices, that is matrix of feature and matrix of updated weights. So here we are using np dot, which we have already used in the gradient descent algorithm. This is our test data, that is the data of test features, and this is our weight. So if we run this cell, we will be able to get the predictions. And now it's time to plot the model on the training data or the data set. So this code is exactly the same code which we saw in our project 1 when we visualize the model performance. So here we have a scatter plot, and on the top of scatter plot, we are plotting our model. That is a model with the test data and with the prediction value. So by running this cell, we can see that our model is trying to fit on the data. It is a good model. It is a good straight line. We can see that it is close to many of the points and error will not be very large. Now it's time to evaluate regression matrices. So we know that we have 3 regression metrics, that is root mean square error, mean absolute error, and R square. So all these values are present in scikit-learn. So from scikit-learn, we will import matrix. Here we are calculating the root mean square. So this is the function matrix dot mean square error. Then we are passing two variable y underscore test and y underscore pred. So for all these 3 matrices, we are passing the same input variables. That is, we are passing the test samples, test labels, and the predicted labels. Let's run this cell. So we can see that y test is not defined. So basically, we need to run this y test, and then we need to run it again. Because at that time, we created y test, but we did not run that cell. So we can see that this is a very good performance. Its value is very high. And we can also see that this root mean square value is very small as compared to our target values. Similarly, mean absolute value is also very small. Now, the gradient descent has been done. We have trained our model by gradient descent. Then we update the weights. Based on the updated weights, we get the prediction from our test data and we evaluate our model. So the gradient descent has been done. And we can see that with the gradient descent, our model has done a very good job. And we can see it performance with the help of these two error and the R square value. Now it's time to compare the performance of gradient descent with least square for this small data set, which has only 30 samples and one feature. So I am importing linear regression from scikit-learn. For least square, I am using scikit-learn. So here I am instantiating my scikit-learn and the variable is LR. Let's run this cell. And here I am reshaping my X. Here I am using LR.fit. So I do not need to append one because I am using scikit-learn, and scikit-learn will take care of all the steps which are present in least square method. So here I am fitting my linear regression to my training data. And here I am printing the intercept, which is the value of a bias, and the coefficient, which is the value of the weight. So let's run this cell. So we can see that this is the value of intercept and the value of weight with the help of least square method. Let's compare this value with the gradient descent method. So when we calculated the weight with the gradient descent method, the value of weight and bias is exactly the same. If you compare these weights value calculated by a gradient descent method with the weight and biases now calculated with the least square, they are exactly the same. Now here is our test data. Here we are, the test data is same, which we have generated for gradient descent as well. Here we are getting a prediction. Now to get the prediction, we use linear regression dot predict so that we can get the prediction from the test data. So fit is used for training and predict is used to get the prediction. So this is the advantage of using scikit-learn. It is the advantage of using a linear regression model from scikit-learn. So it will take care of all the steps of a least square method. So we do not need to apply least square method manually because we are using scikit-learn. Now after prediction, we are plotting our model and we can see that we get exactly the same line which we saw in our gradient descent method. So this lines of code is exactly the same which you saw earlier, and you have already been seen this in our project one as well. So these are the very simple steps of coding. Now it's time to evaluate the performance, that is to calculate the matrices root mean square, mean absolute error, and the R square. So we have imported this again from scikit-learn. Let's run this cell and we can see that these values are exactly same. If you see R square, it is 0.9398. If we go back and see this value, it is 0.398. It is 61975247. So it is 61975247. So we see that here for this particular and simple data set, gradient descent is exactly performance. The performance of a gradient descent is exactly similar to the performance of a least square method. So we cannot see any advantage of one method on the other method for this particular example because we have only 30 samples and we have only one feature. So in this lecture, we learn two things. Basically, we learn how to implement gradient descent in Python for simple linear regression application. After the application of gradient descent, we compare the performance of gradient descent with the least square method. We see that the performance of gradient descent is compatible or exactly equal to the performance of least square method for this data set. So I hope you understood this project. Thanks for listening, and I will see you in the next lecture.